Good morning. This is a new content for you. Case of poles on the real axis. Till now we have done that the poles are lying inside the contour. But in this section we are going to study how to solve the such kind of integrals if the poles are lying on the real axis. Right? So this is the assignment 1 and I am going to prove this integration from 0 to infinity sin of x over x dx is equal to pi by 2. And before that we are going to study some of the new remarks. We are going to use these remarks in the solution. So in this section we will integrate those functions which have poles on the real axis. In such a case we shall follow the procedure known as identity at a point. So the remarks are, first one, you have already know this because we have already discussed this. Recall that negative sine theta is less than equal to negative 2 theta over pi for theta lying between 0 and pi by 2, the closed interval, and e the power negative r sine theta is less than equal to 1 for theta greater than equal to 0 and less than equal to pi, and the radius is greater than 0, strictly positive. Now as negative r sine theta is less than equal to 0, why? Because r is positive, strictly positive, and negative sine of theta is less than equal to negative 2 theta over pi. So their product is less than equal to 0. And if we see e the power minus r sine theta, then this will be less than equal to e the power 0, which is 1. We know that. So e the power negative r sine theta is less than equal to 1. Second, recall that if gamma is an arc where theta is greater than equal to theta 1 and less than equal to theta 2, this theta 1 is your first angle and theta 2 is your last angle, right? When we are going to dealing with the circles. Of the circle mod z minus a equal to rho. This rho is the radius of the circle, and if limit z tends to a, z minus a f of z is equal to any a, where this small a is your pole, right? Then limit rho tends to 0, integration over that gamma fz dz is equal to iota a theta 2 minus theta 1. Now putting the value of a over here, iota theta 2 minus theta 1, now put the value of a, which is limit z tends to a z minus a f of z. This we will solve in the solution, right? So please remember this. Then third one is, if tau is an arc where theta is lying between theta 1 and theta 2 of the circle mod z equal to r, and if limit z tends to infinity, z f of z is equal to a, then limit r tends to infinity, integral over tau fz dz is equal to iota a theta 2 minus theta 1. And iota theta 2 minus theta 1, put the value back of a over here, limit z tends to infinity z into f of z. This is the formula for tau. When you integrate along tau, this is your formula, and when you integrate along this gamma, the small circle, this is your formula. So you have to remember these two formulas, right? Why I am taking limit r tends to infinity over here? Because here for the tau, this r is very, very, very large. But when we talk about this small circle gamma, our rho, the radius, is very, very, very small. When I solve the example, then you will get to know more better. And here are some of the notes. E the power pi iota is negative 1, e the power pi iota by 2 is iota, e the power pi iota by 4 is 1 by root 2 plus iota 1 by root 2. E the power pi iota by 3 is 1 by 2 plus iota root 3 by 2. E the power 2 pi iota by 3 is negative half plus iota root 3 by 2. You can apply the Euler's formula and get all these results. So these are just small notes. And now we are going to start the exercise. Prove that integration from 0 to infinity sine of x over x dx is equal to pi by 2. So we will integrate the function. Of course, I'm having sine function in the numerator. I have to integrate e the power iota z over, instead of x I'm writing z along the contour. Now the contour is changed, right? See, here I'm having the contour consisting of the real axis from, okay, let's start from here, from rho to r, and then the semicircle tau in the upper half plane from positive r to negative r, then the real axis negative r to negative rho, and the semicircle this gamma, that is mod of z equal to rho, in the upper half plane from this negative rho to positive rho. This is the complete contour I'm having. This rho is the radius, and this capital R is also the radius for mod z equal to r, for this tau. For gamma, I'm having this small rho. That is why I'm talking about I have to let r tends to infinity, because here r is very, very large and this rho is small. So r will be tending to infinity and this rho will be tending to 0. Right? This is a little difference. Okay. Now what is the pole? Pole is, see, just take the denominator equal to 0. Pole is z equal to 0. Now since the function is analytic inside and on the contour C, our pole is not lying inside the contour. Pole is z equal to 0. Is it lying inside the contour or outside? Yes, it is outside the contour. Till now we have done the examples if the poles lie inside the contour. But because the pole is now outside the contour and the function is analytic inside and on this contour C, so by Cauchy's theorem, I write integral over this whole complete contour of fz dz is equal to 0. Right? Because we have bent curve at this 0. We have bent and 0 is not lying inside the contour. It is outside the contour. That is why this integral complete over contour C above z dz is 0 here. Right? Now I will split this contour. First I will take from rho to r, then I will take the contour along this tau semicircle, then I will take my contour from negative r to negative rho, and then I solve for this rho. Right, I'm having the 4 parts now. So this contour is splitting up in 4 parts. First from this rho to capital R. So rho to capital R, here I have to take the variable x, fx dx, and then along the semicircle tau in the upper half plane, for that I have to take fz dz, and then from negative r to negative rho, see, from negative r to negative rho. Again I have to take x variable, and then from this circle is your gamma, f of z dz equal to 0. Fine. Okay, now since 1 by z is tending to 0 uniformly as z tends to infinity, and 1 by z is a meromorphic in the upper half plane, so by Jordan's lemma this second integral is always equal to 0. So the second integral I'm writing, because I have to take limit r tends to infinity for the Jordan's lemma, so I'm writing that limit r tends to infinity and integral over this tau e the power iota z. Now instead of fz I'm writing its value e the power iota z over z dz. This is equal to 0. So this implies limit r tends to infinity, integral over in, now this means f of z is equal to 0. So put this value over here. So this value is 0. Right? Okay, now let's check for this tau. Sorry, not tau. Check for this gamma. So applying the formula for this gamma, which we have just now read in remark, what is the formula? That limit rho tends to 0. Please remember, when we talk about tau, we take r tends to infinity, because for tau the radius is r, which is very, very large, right? And when we talk about this small circle gamma, here the radius is very small, this rho. So for gamma we will take rho tending to 0. Rho tending to 0. This rho is your small radius. So limit rho tends to 0, integral over gamma f of z dz. This is equal to, what is the formula? This is iota theta 2 minus theta 1. Limit z tends to a, z minus a f of z, where a is your pole and that a is 0. And theta 2 is your last angle, which is 0. And theta 1 is your first angle, which is pi. See? For this circle, this last angle is 0 and your first angle is pi. The arrow is going from here to here. So complete from here to here, right? So this is pi, and this angle is from 0 to pi, right? So your first angle is, please remember, your first angle is theta 1, which is pi. And the last angle is theta 2, which is 0. So I am writing iota 0 minus pi. Limit z tends to 0. Here it is z minus 0 is z only. Z f of z. So this is equal to negative pi iota. Limit z tends to 0. What is f of z? It is e the power iota z over z. So this is cancelled out. Putting z equal to 0 here, I get minus pi iota, and this is 1. Mark this as 3. So thus letting rho tending to 0 and r tending to infinity in 1. This is your 1. Here we let rho tending to 0 and r tending to infinity. Now putting all the values over here, this value, this remains, second value is 0, third value remains, fourth value is, just now we have calculated, negative pi iota. So I am putting all these values over here. So this implies this. Okay, now here I am having rho to r, letting rho tending to 0, r tending to infinity. So this is from 0 to infinity. The limit is from 0 to infinity. F of x dx, second integral is 0 by Jordan's lemma, and third is from negative r to negative rho. So negative infinity to 0, negative 0 is 0. F of x dx minus pi iota, because this last value is, we have just now calculated, it is negative pi iota. This is equal to 0. So this implies, can I write it as, because this is fx, I am merging these two. So this is minus infinity to infinity. F of x dx is equal to, taking this pi iota to the other side, this is pi iota. Now putting the value of fx in terms of x, yes, which is negative infinity to infinity e the power iota x. What is our function? E the power iota z by z, because I have to write in terms of x now, so this will become e the power iota x over x. Dx is equal to pi iota. Now equating the imaginary parts, please apply the Euler's formula here first. What is e the power iota x? This is cos of x plus iota sine of x. If you put this value here and now equating the imaginary parts, you get sine x. So minus infinity to infinity, I am having sine of x over x dx is equal to pi. And because this sine x over x is even function, so this will be, integration will change to 0 to infinity twice. Sine of x over x dx is equal to pi, as sine x over x is even function. So finally we get 0 to infinity sine of x over x dx is equal to pi by 2. This we need to prove. So we have now proved the result. A little note that every analytic function is meromorphic function, right? Please also take this note as your remark. Thank you so much for watching this video. Do subscribe the channel for the latest videos. Thank you. God bless you all.